I think I am audible. मैडम मेरी आवाज आ रही है? Okay, thank you. So yesterday, continuing from yesterday's lecture, since we have discussed regarding the different types of stresses, both in static and dynamic condition, as well as theories of failure, which were the main constituent of yesterday's lecture. So some of the question and answer part was left yesterday, which will be taking right now. So please concentrate and try to understand the basic concepts as far as static and dynamic loading is concerned. Now, question number 1. A static load is mounted at the center of a shaft rotating at uniform angular velocity. I request all of you to please concentrate on the question and not on the answer first, because in the answer you have to have the logical reasoning for that. A static load is mounted at the center of a shaft rotating at uniform angular velocity. This shaft will be designed for, number 1, the maximum compressive stress, static; the maximum tensile stress, static; the maximum bending moment, static; and fatigue loading. Now, as we can all see, I have written intentionally, the answer of question number 1 is D, fatigue load. Now, why it is a D, which is the most say prominent hint in the question itself? A static load. Now, static load will be there, obviously, no problem. Dynamic and static both can be there, but at the center of shaft rotating at uniform angular velocity. When a static load is kept at the center of rotating shaft, please mind well, at the center of rotating shaft and with uniform angular velocity, because when we say uniform angular velocity, it means it will rotate. And when it will rotate, it will be subjected, due to, say, the load is static, but due to cyclic nature of the motion, the shaft will be subjected to fatigue loading. I hope you are getting the answer. I have started with very simple one, 1 mark question, then we'll go for 2 mark question also. Now, question number 2, fatigue strength of a rod subjected to cyclic axial force. Excuse me. Cyclic axial force is less than that of a rotating beam of the same dimensions subjected to steady lateral force, because axial stiffness is less than bending stiffness. Now, where comes the issue of stiffness here or bending? Let us see to it. See, when we again go through the question, fatigue strength of a rod subjected to cyclic axial force. So this is a rod. It is subjected to axial force, but it is cyclic. Let it be cyclic, na? Tensile compression, tensile compression. So this in this fashion it would be cyclic, no problem. Is less than that of rotating beam. This now beam is rotating of the same dimension subjected to steady but lateral force. Now, the hint is there. The hint is there in the word axial, even though it is cyclic, but it is axial. So, because of absence of centrifugal effect in the rod, the number of discontinuities vulnerable to fatigue are more in rod. Dhyan dijiye, please concentrate on this issue. And D, at a particular time, the rod has only one type of stress, whereas the beam has both tensile and compressive. Even though D looks like a very close answer to this particular issue, But in in detail, if you go for fatigue strength, अभी आ गया, 1 मिनट रुकिए। शेयर स्क्रीन, आई एम शेयरिंग द स्क्रीन नाउ। एप्लीकेशन विंडो। मैडम कब से बंद हुआ है ये बता दीजिए ताकि मैं उतना रिपीट करूं। अभी बस 5 मिनट हुए हैं सर। नहीं तो मुझे मतलब वापस रिपीट करना पड़ेगा क्या? आप कुछ बता सकते हैं लास्ट कहां तक गए थे? नहीं सर। मैं रिपीट करूं फिर से? हाँ सर, कर दीजिए। हाँ, क्योंकि कैसा है, अरे अरे सर नेट बहुत पहले चला गया था, 5 मिनट हो गए हैं। ओके ओके, तो मैं जैसे स्टार्ट किया ना उसके 1-2 मिनट बाद ही नेट चला गया। नहीं तो आप प्लीज बोलिए मैडम, मुझे मैं वापस से ले लेता हूँ। हाँ, वापस से ले। हाँ। मैडम बच्चों का रिएक्शन कुछ दिख रहा है क्या? सो दैट बच्चे अभी भी ज्वाइन नहीं किए हैं सर, मैं अभी डालती हूँ मैसेज फिर से। ओके, मैं मतलब आप मुझे बताइए फिर। सो again I'll repeat this entire episode of question and answer. So again, question number 1, continuing with yesterday's topic. Question number 1, a static load is mounted at the center of shaft rotating at uniform angular velocity. This shaft will be designed answering such questions. Even though it is very simple and 1 mark question generally asked in GATE as well as in IS examinations, a static load is mounted at the center of a shaft. Even though the load is static, but applied or mounted at the center of rotating shaft at uniform angular velocity. This is very important. The shaft is rotating. The shaft is rotating, and some static load is applied. Even though the load is static, but since the shaft is rotating, the fibers will be subjected to cyclic tension and compression known as fatigue. So such type of loading would be considered as fatigue. So the answer of question number 1 is D, fatigue loading. Again, question number 2, fatigue strength of a rod subjected to cyclic axial force. Say this is a rod, but it is subjected to axial force. So this is axial force. This is axial force. Now when we say axial force, sir, it is cyclic also, tensile compressive. So the nature is cyclic. In that case, it is asking that fatigue strength of such component is less than that of a rotating member of the same dimension subjected to steady lateral force. Because why it will be less than this rotating beam? So let us again take this rotating beam. This beam is rotating, this beam is rotating, then rotating beam of same dimension subjected to steady lateral force. Now in this case, load is steady, but the shaft is rotating or the beam is rotating. told you plus and minus sign have got significance with respect to tensile and compressive during a fatigue test or cycle. The R ratio, minimum stress to maximum ratio for this cycle is cyclic loading is. So a simple formula is there. Mean stress is nothing but equals to maximum stress plus minimum stress divided by 2. We are having mean and minimum, so we'll get maximum stress. Now minimum stress divided by maximum stress, you'll get some answer. So minus 0.2 is the answer for this question. Next question in this category, that is static and dynamic loading, is based on the knowledge of stress concentration. As I have told you, stress concentration, when we say stress concentration, this stress concentration occurs at the cross section of a body where there is abrupt change in area, abrupt change in shape. Then at that place stress concentration acts. Now we have got this plate, there is a hole in the plate, so due to the axial loading, due to the axial uniaxial tension of 95 megapascal along the line of this particular hole, so there is a concept that if a large plate is having some hole, then the stress concentration factor will be assumed as 3 to 4. Either you can assume 3 or 4. So we have taken the same reference, and sigma max upon sigma is equal to 3. That is, sigma max is equal to 3 into sigma, and the answer is 285 megapascal. So again, a very simple question, but the logic is stress concentration. The logic is stress concentration, where we can say that this relation would be used to solve such type of problems. Now the next, now this is regarding the theories of failure. My friends, we have learned, we have gone through the theories of failure. 5 prominent theories of used in machine design elements, out of which we have thoroughly gone through the equations first. Now under this particular, I'm trying to explain the graphic representation of different theories of failures. So over here specifically, maximum normal stress criteria, maximum distortion energy criteria, and maximum shear stress criteria. So these 3 criteria or the theories has to be represented with different graphics. So we are having 3 different graphics, so we have to match this. Now as far as maximum normal stress criteria is concerned, since all these theories are applicable to biaxial stress system, when we say biaxial stress system, a system acted upon by 2 different forces along xy or xz or yz, along 2 axes. So in this case, the maximum normal loading would be there in this second diagram M. So we can say that if matching the criteria with the diagram, so maximum normal condition would be matched by this M diagram. The next one is maximum distortion energy criteria. Now since when we use distortion energy, so distortion energy has the graph looks like an elliptical shape or ellipse. So N is the perfect match for distortion energy criteria, that is elliptical shape. And the last one is maximum shear stress criteria, which we generally use for ductile materials. So in that case, since it is in both the planes and the condition is satisfied by the third or the diagram L, so the condition is P with M, Q with N, and R with L, which is satisfied, and the answer is C. So answer of this question number 7 is C. So please mind this particular question very well, because it has been 2 or 3 times it has been asked in GATE and 1 time it is in IES. Again, based on theories of failure, which theory of failure will you use for aluminum component under steady loading? Principal stress theory, principal strain theory, strain energy theory, and the last one is maximum shear stress theory. As we have repeatedly told in the yesterday's lecture, that for ductile material, the only faithful results would be of maximum shear stress theory. So here the answer would be D, that is maximum shear stress theory. Now question number 9. At a critical point, I think this has been asked in summer 18 or 19 examination. So at a critical point in a component, the state of stress is given by sigma x, sigma y. Sigma xy or sigma yx is nothing but shear stress. Yeah, we can represent it by tau also. And all other stress components are 0. That means normal and tangential are 0. The yield strength of the material is 468. 468 is the yield strength. That is very important. SYT. SYT is there. The factor of safety on the basis of maximum shear stress theory is, we have to calculate the shear stress. Based on that shear stress, we have to calculate the factor of safety. Now, what is that particular criteria looks like? Same. Sigma 1 and sigma 2. Since we know sigma x and sigma y and sigma xy, so we substitute this particular equation and get the answer. So sigma 1 is 260 because it is plus minus. So sigma 1 is 260 and sigma 2 is 60. Now, according to maximum shear stress theory, we have to decide the larger of sigma 1 minus sigma 2 by 2 or sigma 1 by 2 or sigma 2 by 2. So we'll calculate all these three values, which looks like that the answer sigma 1 upon, because obviously sigma 1 is larger than obviously sigma 2. So the basic or the simple equation would always be prevailing. Sigma 1 by 2, that is 260. That is 260 divided by 2 is equals to 130. SYT is 460 upon twice factor of safety. The factor of safety is 1.8. The answer is 1.8. I hope you are getting this, because it's a simple calculation wherein we are using the equations, the theories of failure equations. And the last question from my side, as far as this session 1 is concerned, that is a plane strain compression. A forging block is given actually in the diagram, wherein a moving platen is there on the top and the fixed platen is there at the bottom, and the strain in z direction is considered as 0. Obviously, it means that biaxial stress system is prevailing in this equation or in this question. So along x and y, it has been taken the yield strength Sy in uniaxial tension compression of the material of the block is 300 megapascal. This as a yield strength, we have written sigma by t. And it is demanding us that use a Tresca, that is maximum shear stress theory, to solve this particular problem. Now assume that the entire block has started yielding. Obviously it will start because it's ductile material having some yield stress. So at a point where sigma x is 40 megapascal compressive again. If the load is compressive, we have to write it in negative, that is minus 40 megapascal. Now according to Tresca's criteria, tau max is equals to sigma yt upon twice fs. This is the basic equation which we have learned in yesterday's class or in the previous class. For plane strain compression, shear stress may also be written as tau max may be written as sigma x minus sigma y by 2. Now please equate these two equations, and you will get the answer. Sigma y is equals to minus 340 megapascal. Hence the answer is A. Hence the answer is A. As far as factor of safety is concerned, please mind well, everybody. As far as factor of safety is concerned, since factor of safety would be assumed here, so the answer is sigma y is equals to minus 340 megapascal. So I think this is all about the question and answer of our lecture number 1, because yesterday we were short of time, so we have completed it, and I hope you have got most of the questions. So the next we'll go for the lecture number 2 today. So today's, or the second lecture, continuing with the yesterday's class, machine design. Now the outline of this lecture is general design procedure, introduction to joints and design of bolted joint, because in the next lecture we will again be involved in the design of joints only. Now, as far as the general design procedure is concerned, we are much aware that there is no general or rigid rule as to how we should design a product, but general guidelines are given. These guidelines are for help to us as well as to the customers also, as to how we have to put the requirement of a design or a component. Number 1, recognition of need, because without need or necessity, how we can analyze the requirement or the necessity of that particular product to be designed. So first of all, make the complete statement of the need, aim or purpose for which the machine is to be designed. Next, specification and requirement, because generally the need or the demand comes from the customer end, and customer is a non-technical person. A society can give you the demand. Yes, society can explain you the demand, but they cannot specify the requirement. So you have to make this specification, because as a technical person, you have to specify that particular need and requirement. Make the complete specification as to what exactly the customer wants: functioning, size, weight, cost, everything. Again, feasibility study. Check the possibility of success or failure of the proposed project. If someone comes and says to a designer, sir, I'm having a field of 4 acres and I'm having a well at the end of, or at one of the corner of the field. Please suggest me a good value of pump, that is hydraulic pump, obviously centrifugal pump, so that I can fetch the water from the well. So he has given you the demand or the requirement. It is up to us to specify that particular demand and requirement. Also check the feasibility, whether that is possible or not. Sometimes some may demand or some abrupt demand may be there. In that case, you have to check the feasibility of the demand also. After going through the feasibility criteria, okay, this can be done or this can be very well processed, you have to have design synthesis also. Now, selecting possible mechanism, finding the forces acting and their probable effect on the design part, best suited material selection for that. Next, we'll go for preliminary design, wherein drawings will be drawn, layout and overall configuration and functional relationship between various parts will be drawn. Modification, if at all required. Detailed design, obviously the drawing would be. Now, as far as drawings are concerned, we are having the best utilization of technology, computer-aided design, computer-aided manufacturing and computer-aided analysis also. We have to make prototype. Now we can go for animations also. So we all are much aware about the facilities provided. Next is design for production. Prepare the final drawing, mentioning the complete details such as process involved, material, tolerances, etc. Now, this is a general guideline or the outline of design procedure. Now, in this lecture, we have to concentrate on introduction to mechanical joints, that is design of joints. Now, as far as mechanical joints are concerned, it is basically a system of connecting one or more mechanical part, one or more mechanical elements, so that some load can be transferred, some pressure can be transferred, so that some motion can be transmitted. So all these things, all these connections, all these joints are to be studied under the heads of these three classification. Number one is types of joint, that is how the joints are classified. So this is a very simple classification as far as different types of joints are concerned. Number one is permanent joint. Number two is semi-permanent joint. And number three are temporary joints. When we say permanent joint, both the connecting parts are permanently joined. Both the joint and joining components are required to be completely destroyed for disassembling. Sorry. This is the logic, this is the point wherein we say that this joint is permanent. What is that logic? We require to destroy the joining element as well as a joining component as well as joining element. So welded joint is the best example for permanent joint. Brazed joints, brazing, soldering also, these are the example of permanent joints. The next is semi-permanent joint. Both the connecting parts are fixed by a permanent joining element which is required to be destroyed for disassembly. Parent metal will not be disturbed. Let us take the example of riveted joint, wherein riveted joints, only if you want to disassemble that joint, in that case only the rivet must be required to be destroyed. Else and the last one, again, which is very important, temporary joint. Both the joining elements can be easily connected and disconnected. We generally say readily connected or disconnected without damaging the joining component as well as parent metals. Example, bolted or screwed joints, knuckle joints, quarter joint, turnbuckle. So these are the general example of temporary joints. Our aspect is to cover design of bolted joint, generally known as screwed joints also. A screwed joint is mainly composed of a nut and bolt. I am using a very simple terminology because nut and bolt we all are much aware or say much acquainted as compared to bolted or screwed joints. So nut and bolt joint, it is widely used in fastening over a large area of application. A large area, automobile, domestic, industrial, in machineries, lathe, milling, everywhere you will have this temporary joint known as a screwed joints or bolted joint. Now there are some important terms in screw threads because as far as design is concerned, we have to go through this particular terms. Number one, that is the nominal diameter of the screw thread, and there comes the threads. So these are the threads. Generally these threads are known as V threads, and the angle included between the threads is generally 60 degrees. The distance between two consecutive either crest or between two troughs is known as pitch. Crest is the upper tip and the root is the lowest tip of the thread. Again, this one is the flank. This portion, solid portion of the bolt, is also known as a shank. Now, as far as diameters are concerned, there are three basic diameter designation which we provide to the screw threads. Number one, major diameter, the outside or outer diameter, also known as a nominal diameter. The major diameter, nominal diameter, outside diameter, all three are the same. The next is minor diameter. This is minor diameter. Inner diameter, this in diameter, minor diameter. Minor diameter, or smallest diameter? One and the same. And the third diameter is pitch diameter, which is nothing but the approximation of mean. That is a mean diameter, pitch circle diameter, or simply pitch diameter between major and minor. So this is pitch diameter. So these are the important terminologies which are to be used during the design of the screwed or bolted joints. The next thing which will come across during the design process is the designation of screw threads. How these bolts are designated. If you go to a shop or a market and you ask for some bolt, so you have to tell him, sir, you please give me the bolt of 10 mm. Now the 10 mm diameter bolt he or she will give you definitely, but if you pronounce M12, M14, it looks like that it is the designation at the correct technical designation of diameter and the bolt. So bolts are generally designated by letter M followed by the diameter in general. M12, M14, M20, M24. These are the general. Now again the threads have got three different types of classification: coarse thread, fine thread, and normal threads. Also, some bolts require tolerance grade to specify or to designate the screw thread. In that case, we may write it as M6-8D. So here the tolerance grade is added to this particular designation. Now, the next is modes of failure. That is very, very, very important, since we are about to solve a number of numericals over this particular design of bolted or screwed joints. So we will see the different failures, possible failures in the design of bolts. So this is the basic structure of any bolt, which is connecting two plates, which is connecting two plates by a nut and bolt. Now, the failures. Number one, tensile failure of bolt. Maximum tensile stress induced in the bolt may be given as load upon area. This is direct stress. Now, which diameter is to be considered? Now, please concentrate core diameter. I again repeat, the weakest diameter of the bolt is core diameter. So again, we'll have to go through the diagram. Since this minor diameter is nothing but core diameter. The another third name, minor, minimum, and core diameter. So this is the minimum diameter of the any screw thread which is vulnerable to the applied load. So we have to design on the basis of this smallest diameter, pi by 4 DC square, core diameter. In addition to this, threads of bolt can also fail in shear and crushing. Obviously, it will be looked after. Shear stress, shear failure of the thread. Maximum shear stress, again load per unit area. Now, in this case, the shear failure of the thread may be calculated in this fashion. So this is the formula which is available with us, where again this applied or induced shear stress must be less than the allowable shear stress everywhere. So where n number of turns, the width of the thread in terms of thread. DC is a root or core diameter. Now, if you want to calculate the height of bolt, H is equals to N into B. Again, the same can be well written in this equation. Next is crushing failure of the thread. Now, in the beginning itself, since you might have studied in SOM, there are different types of failure, but still I want to just revise in short span of time. When we say tensile failure of the threads will be subjected. Say this is the thread. Say these are the threads. The threads will be subjected to tension. The threads will be subjected to tension. In that case, the cross-sectional area would be sufficient enough to hold that particular load. Now here also in shear, because in some of the cases, like you take the example of some some foot plates or some truss plates. In that case, the bolt will be fitted along in this fashion. Along these two plates, the bolt will be perpendicular. Now these plates will be pulling each other. In that case, this particular bolt will go in shear, a direct or simple shear. The third one is crushing, the localized compressive stress failure of the bolt. That's why when we say localized compression, the area, if you are observing and concentrating, pi by 4 d square minus dc square. Yes, again I want to go back to that particular diagram wherein we have studied. Yes, sir. So this is generally known as DO or DO minus DC. It means the effective diameter. This is the effective diameter which is supposed to be taken into consideration when the crushing occurs. The next one, shear failure of bolt. When we say the bolt are in shear failure, when it is subjected to tensile, see, we have seen shear failure of thread, because threads are the most vulnerable and the weakest portion in any thread. Say if the bolt is there having both shank portion, I am again repeating, shank portion and the threaded portion, then in that case also the weakest part will be along. That's why again the same formula, pi by 4 dc square, a simple shear of the bolt itself. Now one relation we have to keep it in mind for calculating this core diameter or the nominal diameter. If some table is available with us in the design data books, then it is okay. Otherwise, we have to use this relation, empirical relation, DC is equals to 0.8 times of D to find the nominal diameter. Because at the end of the calculations, we have to find the nominal diameter of any bolt. So we have to have this. Next, pre-stressing in bolts. Now, if you are having number of times, you might have experienced this. If the tire of the bike gets punctured, in that case, we start with the unscrewing of that thread or the tire of that bike. In that case, the very first issue is, after the completion of that particular process of puncture making, we have to tighten those nuts and bolts. Initially, what we do in any case, in any nuts and bolts or the screws, we initially tighten it. The torque applied essentially puts initial tension in the bolt itself. How much it should be so that the joint should not get disturbed. So a general value or the generalized value is given. So in fluid tight joints, maximum 2840. Please mind this well. Okay, Newton into some nominal diameter. Obviously, in terms of nominal diameter will be there. So this much force or initial tension is restricted for the initial compensation. So that is the nominal diameter of the bolt, and initial stress in the bolt can be calculated. Now, this is nothing but the design of bolted or screwed joints. And the most important part, as far as the numericals are concerned, is the eccentrically loaded bolted joints. Wherein, when we say eccentric loading, it means a very simple element, wherein if the applied load, I can take the example here, say if this is the center of this particular or the center of gravity of this particular cap, then if I am applying some load at the center, it is known as axial load. But at the same time, if I am applying a load other than axis of this particular object, then the distance between the line of action of force and the axis of this particular body is known as eccentricity, and the applied load is known as eccentric load. So over here, the bolted system, this is the system of bolt, wherein some plate is fixed with some 4, 6, 8 different types of different number of bolts to some wall, to some plate, to some truss member. Now this can be fixed in the first manner is eccentric load acting in the plane of bolt. Now when we say eccentric load acting in the plane of bolt, how does it react? When we say how does it react, it means that how the bolts will be subjected to different types of stresses and loading. To begin with, and I'm taking a simple example here, say for simple case of understanding and nothing but so that we can very well learn. Now say this is a plate which is fixed on this column by 4 number of bolts. Now these bolts are, the axis of the bolts are perpendicular to this surface. Now I'm applying some load, but prior to or before applying some load, this plate will try to go down under gravity. It will try to fall under gravity. So the very basic job of these bolts is to restrict the motion of this particular plate which is about to going, say, down under gravity by virtue of its own weight. So this will induce primary shear force in all the bolts. That's why if you concentrate on the presentation, P1 dash, P2 dash equals to P3 dash equals to P4 dash, the primary shear load or shear force on each bolt will be calculated equals to total load P upon number of bolts. So first it will resist the entire total load acting on the all 4 bolts, 6 or 8 depends. What next? What next? So this is called primary shear. The very next moment will be, since I'm applying the load here, it will try to, now please concentrate, it will try to topple or it will try to rotate this plate. Yes, this particular action or moment where this load P into this distance E, known as eccentricity or eccentric distance from the center of gravity of this particular bolted system, then this P into E will try to overturn this bracket and it would be shown in this fashion. So due to this overturning of the bracket, secondary shear force will come into picture. But this secondary shear force will be nothing but the moment, developed at each bolt with respect to the CG of the bolted system, CG of the bolt system. So if say for example I'm having P1 double dash P1 double dash, then P1 double dash multiplied by R1 would be the turning moment which develops a secondary shear stress. P2 dash R2, P3 dash R3 and P4 dash R4. So it is assumed that the secondary shear force in any bolt is proportional to its distance from the center of gravity. So in proportion we have written all these 4. Now considering C as proportionality constant, where C is a factor basically, and that factor is nothing but P into E upon R1 square plus R2 square plus R3 square plus R4 square. You can directly say take up this formula in this fashion. So therefore, along this, we can say that P1 dash can be written as this C into the distance. This C into some distance R1. P2 dash this C into some distance R2, because we have found out this constant of proportionality as P1 dash. So with this P1 dash, you can calculate again the P2 dash, then P3 dash and P4 dash. And then again, you'll have to select. Now please mind well, you'll have to select the maximum. You'll have to select the maximum secondary shear force. Then since the primary is also shear, secondary is also shear, so you have to add both these stresses. First, I'll call it as say P1 dash, then here it is P1 double dash. So you have to calculate, or you have to sum up all these stresses, then find out the maximum shear where bolt is subjected, at what shear is occurring, whether at bolt 1, bolt 2, bolt 3 or bolt 4, and that maximum is to be equated. Is equals to tau is equals to total P, that is P mean or P effective divided by pi by 4 DC square, and we'll get pi by 4 DC square, and we'll get the diameter, core diameter of the bolt. And with the formula DC is equals to 0.8 times of D, we can very well calculate the nominal diameter of the bolt or the screwed joints. So this is the very basic element of design of eccentrically loaded bolted joint. So tomorrow, in the next lecture, we'll proceed further with the numericals and more example, more second type of eccentrically loaded, that is in the plane and perpendicular to the plane. So thank you so much for today's lecture. Tomorrow we'll continue the same topic in the next lecture with design of welded joint and design of riveted joint also. Thank you, sir.